Hello and welcome to this video about generalized eigenvectors. One of the reasons that we try to find the eigenvalues and eigenvectors of a matrix is so that we can diagonalize them and so perform functions on them, like square roots and exponentials. But not every matrix is diagonalizable, because some matrices are degenerate or defective, meaning that not enough eigenvectors can be found. This happens when any eigenvalue occurs twice or more as a solution to the characteristic polynomial, and then there is the possibility that not enough eigenvectors can be found for this particular eigenvalue. So we need to have a different approach. Instead of diagonalizing this matrix, we'll reduce it to Jordan canonical form instead, which can be enough to find functions of this matrix. A matrix in Jordan canonical form has all of its eigenvalues in the diagonal region like a diagonal matrix, plus some extra ones on top of some of the repeating eigenvalues, which prevents them from having some of the best properties of a diagonal matrix, which is that the square root or other function of it is equal to this function applied to all of its diagonal elements. So to study what generalized eigenvectors are and how to find them, we'll look at various sorts of matrix. The best one to start with is a matrix which is already in Jordan canonical form, which is not similar to any diagonal matrix, and is in a very simple form so as to observe what is happening. We'll call this matrix that we'll be studying A, and one of its eigenvectors is called V, and its corresponding eigenvalue can be seen to be 3, and is called lambda. And since it is degenerative, then it has a generalized eigenvector called U that corresponds to V, and also shares this eigenvalue of 3 with V. Since V is an eigenvector of A, then it is a non-zero solution to this equation here, and this 0 is the zero vector, which is why it has a little squiggle underneath it. This equation can be more accurately written as this kernel equation, where V is an element of this set, but we won't need this equation for now. We can substitute all of these matrices and values into this matrix equation to get this equation here. So then, after subtracting these two matrices, we'll get this equation. All of the elements in the column of this matrix corresponding to the row in this vector which contains a 1 are equal to 0, which guarantees that the solution will be the zero vector. And so it is equal to the zero vector. This particular 0 is highlighted because it was the only element in this vector which could be non-zero. We'll write out the zero vector in squiggle notation to complete this calculation. Now to observe the behavior of a generalized eigenvector. We'll use the same Jordan canonical matrix as before. The generalized eigenvector will satisfy this equation. This sort of vector is not in the kernel of this particular matrix. The product of it will be its corresponding eigenvector. So this is a rank 2 generalized eigenvector. Multiplying the square of this matrix by this generalized eigenvector will be equal to 0. So U will be in the kernel of the square of this matrix. Substituting all of these values into this first equation will give us this matrix equation. Adding these two matrices together will give us this equation, so that zeros occur in the diagonal corresponding to these eigenvalues and eigenvectors. You can see that there is a 1 in this column that will multiply by the 1 in this vector to give us a non-zero vector. After multiplying these matrices together, these two 1s multiply together to give us this 1 circled in red, and this vector is equal to the eigenvector v, which completes this equation. So now to look at a more complicated example of a non-diagonalizable matrix, and how to find a generalized eigenvector for it. Because this matrix is an upper triangular matrix, then the eigenvalues are just the diagonal entries. One of these eigenvalues occurs twice, so there is a possibility that it doesn't have enough eigenvectors to diagonalize it. After finding the eigenvectors that correspond to these eigenvalues, we find that the eigenvalue that occurs twice has only one eigenvector. Now we have to find a generalized eigenvector for this eigenvalue. This matrix cannot be diagonalized, but it may be transformed into the next best thing, called a Jordan canonical form. But we need to find a generalized eigenvector to do this. We'll use this equation to find it. This generalized eigenvector is not in the kernel of this matrix, but it is related to the first eigenvector in this way, and is called a rank 2 generalized eigenvector, because the product is equal to an eigenvector. An eigenvector may also be called a generalized eigenvector of rank 1. So now we'll substitute all of the values in, and the generalized eigenvector u can be made equal to this vector a, b, c. And after simplifying this matrix, we get this equation, which won't be like solving the matrix equations that we are used to solving, because this matrix is not invertible. Now we have to solve this matrix equation with a non-invertible matrix. We could think of solving it by transforming it into an augmented matrix. We would then perform row operations on it, so as to get its reduced row echelon form. Notice that the right-hand column is not affected, because the first row wasn't added or subtracted from anything. So then we'd transform this augmented matrix back into this matrix equation that resembles an equation in algebra. Then we'd multiply the matrix by the vector to get this equation. Then we'd unpack this vector equation to get these two algebraic equations. Notice that a can be any number, and the equation will still be correct, because there are only zeros in a's column. So we can write a unchanged in this vector, and write in the values of b and c that we've found. Then we can separate out the a component of this vector. Notice that it is a scalar multiplied by the eigenvector that we use to find it. So this value is in the kernel of this equation, and will give a value of 0, and can thus be ignored. So this will be the value of the generalized eigenvector that we've been trying to find. We can see that this matrix A is similar to this Jordan canonical matrix, because they satisfy this equation given here. The change of basis matrix is made up of the eigenvectors and generalized eigenvectors of the matrix A. These eigenvectors have to correspond to the eigenvalues found in the Jordan matrix, and the generalized eigenvector has to stand next to and on the right-hand side of the eigenvector that has been its seed. We can then evaluate the inverse of this change of basis matrix. We can then find any function of this matrix by finding this function of the Jordan canonical matrix that it is similar to, and multiplying it by the change of basis matrix, like this. I got this on the internet. It is the function value of a Jordan canonical matrix. It is a bit more complicated than that of a diagonal matrix, but it can be done easily. All of the values in the same Jordan block can be calculated according to this pattern. Here is another example of applying a function to a Jordan canonical matrix for blocks that are 2 and 3 elements wide. Here is a more general example. Very high derivatives have to be calculated. So here is a second example of a matrix that we need to find generalized eigenvectors for. This one needs 2 of them for this one eigenvalue and eigenvector. We firstly need to calculate this matrix, which was needed to find the eigenvector for this eigenvalue. And so this is what it is equal to after evaluating it. The generalized eigenvector u has to satisfy this equation, where v is the eigenvector that is its seed. It is a rank 2 generalized eigenvector because it has an eigenvector as its seed. We can then substitute all of the values into this equation to get this matrix equation. We'll let the column ABC be equal to the vector u. So we have to apply row operations to both sides to reduce this matrix to reduced row echelon form. It would be helpful to convert this equation to this augmented matrix, where the column would equal the right-hand side of this equation. This is the augmented matrix in reduced row echelon form. Then we can convert this augmented matrix back into this more algebraic looking matrix equation. I'll just write this equation back up here and clear the rest of the screen. Multiplying this matrix by this vector gives us this vector. Notice that the lowest row is all zeros. This means that this equation can be solved for the generalized eigenvector u. Taking all of the variables a, b and c out of this vector equation gives us these two equations for a, b and c. A can be expressed as this in terms of c. Since a and b have leading ones in their columns, then they'll be assigned numerical values, and the variable c will be free to take on any value. We can separate these two vectors out like this. Since the second vector is part of the zero solution, or kernel of matrix A minus lambda, it can be ignored, and we'll set the generalized eigenvector equal to this value. Now it's time to find the second generalized eigenvector. This one is set to be called W, and is seeded by the first generalized eigenvector u. It is for this reason called a rank 3 generalized eigenvector. After substituting all of the values into this equation, we get this matrix equation. We'll set the column GHK to be equal to this generalized eigenvector W. We'll apply the row operations to both sides of this equation. This can best be illustrated by converting this equation into the augmented matrix as shown. Then we'll get the reduced row echelon form of this augmented matrix. And then we'll convert this augmented matrix into this algebraic looking matrix equation. We'll multiply the matrix by the vector to get this column vector. Having zeros at the bottom shows us that this equation can be solved. Then we'll extract these two algebraic equations from this vector equation. We can get the value of g in terms of k. So this is what this column vector is equal to. Since there was no 1 in the k's column, then we'll let k be equal to anything. We can separate out the two vectors like this, one of them being multiplied by k. And since this vector that's multiplied by k is part of the kernel or zero solution, we can then ignore it and set the generalized eigenvector equal to this. So this is how the change of basis matrix is constructed, by placing the generalized eigenvectors in each column in the order that they were generated by each other. V was found first, then U, then W. You can see it more clearly here, where all of the matrices and vectors are substituted in. All of these generalized eigenvectors are placed one after the other in order of rank 1 being the eigenvector itself. So now to write some computer code to find the generalized eigenvector of a matrix. We'll start at solving this augmented matrix that is in reduced row echelon form, which is not as simple as solving most other matrix equations, because the left-hand side is not invertible. To examine what is actually happening, we'll firstly transform this system of equations from augmented matrix notation to algebraic matrix notation. Multiplying the matrix with the vector gives us this equation. We can then extract these two algebraic equations from this vector equation. And this first equation can be rewritten like this so as to make B the subject of this equation. You can probably see by now that B and D correspond to the columns that contain the leading ones in this matrix. The solution can be rewritten like this, since A and C can be nearly anything without affecting the solution. So these two vectors belong to the zero solution, and for our purposes may be ignored, leaving this as the solution to our equation. You can easily see that the leading one in the matrix that corresponds to the number 5 in the right-hand column of the augmented matrix corresponds to the second column of this same matrix, and since B is the second variable in the solution matrix, then the second row in the solution vector is set to be 5. And similarly for the number 7 being placed in the fourth row of this vector. So this gives us a clever trick to find the generalized eigenvector from this system of equations. Now to have a look at some computer code that solves this augmented matrix equation that doesn't contain an invertible matrix, but this messy non-invertible matrix. You can see that it can be solved because it has all zeros on the bottom two rows. If there was a non-zero entry in the right-hand column where there was all zeros in the rest of the row, then no solution would be able to be found. The variable n would be preset to the number of rows with non-zero elements in them, which contain all of the information for the generalized eigenvector. So the first thing to do is to create a loop that steps through all of these non-zero rows, and I is the variable that points to each row in this loop. Then j is equal to the column position of the leading one of this particular row. So the jth element of the generalized eigenvector u is equal to the ith element of the eigenvector v. We can see that in the first row I is equal to 1, and the column position of its leading one is 2. So the first element in v, which is 5, is placed into u as its second element. Similarly, we can then place the second element of v, which is -7, into the fourth position of u. The other elements in u must be set to 0, which can be easily done by presetting all of u's elements to 0 before it enters this stage. As a final example, I'd like to look at a Jordan canonical matrix to see the effect of multiplying it by its eigenvectors and generalized eigenvectors. And here are all of its eigenvalues, eigenvectors, and its generalized eigenvector. So here are the equations showing that multiplication by A is the same as multiplying it by its eigenvalue, and showing the special equation for its generalized eigenvector. We could build up a matrix out of columns of these vectors like this. We could start substituting the matrix and eigenvectors into this equation. And this is what the column vectors look like when multiplied by their corresponding eigenvalues, which gives us the same matrix A back again. And here it is without column dividers. So I hope that you have enjoyed this video and have learnt a lot from it, and I wish you all the best in your efforts to study this sort of mathematics. Please leave your thoughts in the comments and click the subscribe button if you wish to view more of these videos.